Thank you for the introduction, and I would like to thank the organizers for allowing me to reschedule my presentation at such a short notice. So what I would like to present today are some results that I've obtained in the recent years in the field of surrogate modeling for frequency domain applications. And I'd like to mention that many of the things I will discuss are joint work with Fabio Nobile from Lausanne and Francesca, who just presented this morning some related topics. Now, as some of the previous talks today have spoken about, like we will consider frequency domain applications. And I don't need to introduce the Helmholtz equation to this audience, but this is the prototypical example of frequency domain application that we will have in mind, which is obtained, of course, as Fourier or Laplace transform of the wave equation. And depending on what kind of boundary conditions we endow it with, we might have different classes of problems. We might be modeling different classes of physical systems. So if we have Dirichlet or Neumann conditions, for instance, we might be in the case of cavity problems. And just to fix the notations, I would like to say that omega throughout my presentation will be the angular frequency. It's a third meaning that we assign to the letter omega today, so that's nice. And U will be the solution of the PDE. And of course, U will depend on frequency, both because the Helmholtz equation itself depends on frequency, but also because the right-hand side and the boundary conditions, the boundary data, might depend on frequency too. Or a different class of problems might be that of scattering problems, as we've seen in the previous talk. And in this case, the equation is usually stated on the outside, on the exterior of a certain compact D, the scatterer. And we have usually different conditions on the boundary of the scatterer. So usually we have Dirichlet-Neumann or Robin type conditions on the scatterer, depending on the type of scatterer. And then we need some closure, some condition for closure at infinity. And usually this is done with the Sommerfeld radiation condition. But of course, we're doing numerics, so we need to truncate the domain, at least in finite elements and finite differences. So usually what we do, the simplest thing we can do is to take the intersection with a ball of sufficiently large radius, and then we impose some condition on this fictitious boundary. The one I'm showing here is just a very simple, very crude approximation of the Sommerfeld radiation condition, which is just a Robin condition, an impedance condition where you see that the frequency actually appears here. But of course, we might have some more sophisticated ways to prevent reflections from infinity. For instance, we might have a perfectly matched layer, which essentially the way this works is that we enlarge a bit our computational domain, and then we solve a Helmholtz equation in this enlarged domain, but we introduce some dissipation to ensure that we don't have any reflections from this fictitious boundary. And here, the PML, I put a dependence on omega because usually the amount of dissipation that you need to add depends on omega as well. But the dependence on omega is in general more complicated than just, you see, a linear dependence as in the Robin type condition. Anyway, you can put basically whatever you want here, because most of my presentation actually will just consider a very general framework, which is the one that I'm putting here. So we have this scalar complex parameters frequency, omega, and then we have the first equation, which is the one I described until now. I'm going to call it the state equation. And this operator L might be the Helmholtz equation, but it will also encode the boundary conditions. In many applications, what we're interested in is actually not the state U itself, but a functional of U, which in this slide I assume to be linear. So it's just a measurement, for instance, or an average or something like this. But in general, I mean, more complicated settings might be nonlinear. For instance, it might be norm of U. Okay. And here you can see that I'm already considering the finite dimensional setting. So I'm assuming that somebody has given us a discretization of our problem, finite elements, finite differences, for instance. And the state as dimension NH. And in many applications, NH has to be large because, as we've seen in Francesca's presentation, we need to be able to resolve the oscillations. So the larger omega we take, the more refined the grid is going to have to be. And in this presentation, just like in Francesca's, the overall purpose is going to be to approximate one of the two maps that you see here. So either the state map, so given a certain frequency, we look at the solution of the problem, or the quantity of interest. So given a frequency, we look at the functional of the solution. I will say more about why we're trying to do this. But just for exposition, I will consider often a simplified version of this problem, which is like very much simplified. So you can see here, I'm assuming that the dependence on omega of the operator L that before defined our right-hand side there is actually linear in omega, so that I can use the notation and many of the tools from linear time invariant frequency domain systems. And I'm sure you've seen this this kind of problem before. It's just the Laplace transform of a first order linear time invariant system. But I will do this only for exposition. Most of the things I will say will not depend on the specific type of omega dependence that we have. Now, to explain a bit more what we're interested in the end, we're interested in what's called the frequency response of the system, which it is just an umbrella term to say a function of omega in some sense. And as I said before, we are interested in the state or in the quantity of interest. But in most cases, for illustration purposes, I will show the normal view as the quantity we're interested in, which somehow gives us information on the magnitude of the solution of the problem, of course. And if the system is of this very simple kind that I introduced just before, we can actually obtain in closed form what the solution will look like. You can see that to obtain the state, we just need to take the inverse of this matrix pencil, omega e minus a. And of course, to take the functional, we just apply the row vector L essentially to this solution. And under some spectral conditions on the matrix pencil, omega e minus a, essentially we have to assume some kind of regularity of the spectrum of this pencil. Then we have a decomposition that's called a heaviside expansion of the state. This is a very specific heaviside expansion where all the exponents on the denominator are equal to 1. So all the poles are equal to 1. And we have this kind of expansion, for instance, if we assume some kind of symmetry of our problem. So if we take a cavity problem, for instance, we know that we have this kind of expansion. But in more general cases, we might have exponents here in the denominator. So the resonating frequencies lambda I might appear as poles of order larger than 1 in general. And as you see, like if we sample, if we look at what happens too close for omega too close to one of the resonating frequencies lambda I, what we have is a spike in this plot. So the solution goes off to infinity. The problem becomes singular, and at the resonating frequency, we cannot solve the problem. Of course, this assumes that the resonating frequencies are exactly on the interval of frequencies that we're considering. So they are real, which happens for the cavity problem, for instance. But in general cases, we might have some kind of damping. And this happens, for instance, in scattering problems, where the poles are not on the real line, but they are in the complex plane outside the real line. And instead of having peaks, instead, what we have are some hills that are smoother, and there the solution doesn't go to infinity. Now, what I'm hiding behind this picture, of course, is as to obtain every single point in this plot, I had to invert this matrix omega e minus a, right? And if the system is large, if the resolution of our numerical grid, spatial grid, is very large, or we're using high-dimensional polynomials in a finite element discretization, for instance, then this is going to take some time. And what we're trying to do with model reduction, as Francesca said this morning, is that instead of solving the problem at all the frequencies where I want to have a point in this plot, essentially, what we do is we spend some time to train a surrogate. And in this presentation, surrogates are going to be denoted by tilde. Okay, we train a surrogate, u tilde, and then we evaluate the surrogate instead of evaluating the function itself. And if the evaluating the surrogate costs less, much less, than solving the original system, then we can hope to achieve some computational time saves. And of course, we need to have a surrogate that's good at what it does. So we need to have some accuracy, a good accuracy in the approximation of the original function u. All right, so this is just a small part of the picture, because of course, what we're really after is not just the dependence on the frequency, but we're also going to have some parameters, theta. They're not just one, they could be a collection of parameters, could be material parameters, could be geometric parameters, as we've seen just before. And you can imagine that changing the parameters will change the frequency response of the system. So this can be, for instance, something that we want to do in UQ. We have stochastic parameters, some random variables, gamma, theta, that encode some unknown information about the system. And we want to try to do some UQ on the response of the system. Now, I will not talk about this much in this presentation because I gave a presentation in the second workshop, and you can find it on YouTube, and we can talk about it, of course, if you're interested in the setting. I will try to give an overview on how we can use what I will present actually in the parametric setting. Now, as the title suggested, we are trying to do all of this in the so-called non-intrusive paradigm, where essentially we are assuming that we're not necessarily assuming that we are able to access the structure of the system of the PDE that defines our problem. So for instance, if we have a linear time invariant system, we are assuming, we're not assuming to be able to access the blocks E and A of the system or the right-hand side, for instance. The only thing we can do is we have this black box mysterious function that we can feed a value of omega into, and we obtain the corresponding solution. Okay, this is going to be a black box solver, for instance. And of course, this means that our model reduction approach will have to be data driven in the sense that the only thing we have to build our surrogate with are the samples of the function, no information on the system itself. Now, why are we interested in non-intrusive methods? Well, there are several reasons, and here I just put 3 of them. For instance, the first reason might be that the solver that you use for the Helmholtz equation is black box, so you cannot touch it. You have no idea what goes on under the cogs here. Or it could be that actually what we're trying to solve is a problem that's too complicated to be able to put it in. Essentially, we cannot put the problem in the framework that I discussed before. We cannot write it as a linear time invariant system. And we'll see why this can cause problems for intrusive methods in just a minute. But the real reason why the non-intrusive paradigm was actually explored was that we might want to apply our model reduction technique not to results of numerical simulations, but to experimental data. Okay, so let's imagine that instead of having a black box solver here, so a computer that tells us what the answer is, we have like a scientist actually performing an experiment, and that's the value that we are given to start with. Okay. And maybe we don't even have a model to base our surrogate model on, right? Okay, so to start, I would like to discuss some of the intrusive methods for model reduction, just to give you an idea of how these surrogates can actually be built in practice. And here I'm putting just some of the names of people that have studied this field. I missed many more, so I hope you don't get offended if your name is not here. So the way intrusive model reduction works is usually by projection. And to understand what we project, let's go back to the original equation in the very simplified linear time invariant case. You can see here that the main cost in evaluating the quantity of interest y is going to be the inversion of the very large matrix omega e minus a. So what we want to do is we want to reduce this cost, and the simplest way to do it is to actually project the problem onto a lower dimensional subspace. You can see that we are doing this with this projector P, and it's transposed, pre-transposed, and you see that it appears 4 times. Here it appears we left project the right-hand side, we right project the measurement operator, and we left and right project the matrix pencil, omega e minus a. And you can imagine that since here this matrix pencil is just linear, a sum of 2 terms, we can actually factor the product in, and we obtain a system of reduced size of this kind. Essentially, if P has only few columns, let's say n star columns, then the resulting system that we get here is actually of size n star by n star. And you can see that actually evaluating this surrogate y tilde is going to require the inversion of a much smaller matrix than the original one. Okay, it's important to know that this is dense, whereas this might be sparse, but if the dimension is sufficiently small, then we don't really care about that. And one of the important consequences of this is that actually we preserve the structure of the original problem in the sense that the original quantity of interest, for instance, will had this kind of meromorphic dependence on omega, and the same kind of dependence can be observed in the surrogate model, except that now the resonating frequencies are going to be replaced by surrogate resonating frequencies that are just the eigenvalues of this reduced matrix pencil. And the residues, again, here this P star I is an approximation of a projector onto an approximated eigenspace. Now, how do we define the projector P? Because that, of course, you can imagine is the crucial question here. Different P's will give us surrogates with different qualities. And there are many ways to choose them. In this presentation, I will mostly focus on data-driven ones because they are more similar to the overall structure that the overall algorithm that we're after. And in particular, I will consider the proper orthogonal decomposition and the reduced basis method. So I would like to give you an overview of this, and this is a single slide on that, essentially. And this is the skeleton of the algorithm of the simplest method you can imagine, the simplest projective method you can imagine, which is called the method of snapshots. And many of you have seen it already, I think. So the method works like this. So first of all, we take S samples of our function U, of the state U. And here I'm representing different samples, and they are taken at different frequencies, of course. But and this is going to be important in the sequel. We have to fix in advance how many samples we take and where we take them. Then we take all the samples and we stack them as columns of the so-called snapshot matrix. And then the only thing that's left to do is we define P as the orthogonal projection onto the range of this snapshot matrix. Okay, this allows us to define our projector P, and that's essentially the algorithm in a nutshell. Except that, of course, for stability, we might want to find an orthogonal projector in a reasonable linear algebra way. And to do this, we compute a QR decomposition of our snapshot matrix. And to the same, I would like to mention, and because this is going to be important in the future, we have to consider the snapshot Gramian matrix, which is a square matrix, a low-dimensional matrix, which has been considered also in Francesca's talk before. And it's just a matrix that contains the inner products between the different snapshots that we've taken. Now, as I said just now, we need to fix in advance for this method the number S, so the number of samples we're going to take and where we're going to take them, right? But here we come back to the title of my talk. The reliable in the title is somehow trying to ask, like, is there a more general, a more robust way to approach model reduction, in the sense that if you're given a certain problem in a certain range of frequencies, you're not going to know in advance how many samples are necessary to obtain a certain accuracy of your surrogate, right? And with projective methods, the answer is actually yes. And the simplest version of this kind of adaptive algorithm is the so-called greedy reduced basis algorithm. And just for reference, I would like to mention that when I talk about adaptivity here, I'm not talking about space adaptivity. That was Francesca's talk. Here, we're just trying to adapt the number of snapshots. So we're trying to adapt over omega only, not over space and omega, just omega. Now, the way the greedy algorithm works is fairly simple, and I will try to explain it using this cartoon on the right. Let's say that we're trying to approximate this black function here. So what we start with is a very coarse surrogate. So we have this U tilde that, just for illustration purposes, is just approximates the function U by a constant function. Then, of course, we need to ask the question, is the current surrogate good enough or not? And for that, we look at the approximation error, just the difference between the surrogate and the actual quantity we're trying to approximate. And we look at the point where the error is maximum. We look at the value and we say, well, this value is too large, is larger than a certain tolerance that somebody has prescribed. So what we do is we just take this point where the error is largest and we add it to our training set, okay? So we improve the quality of our surrogate by adding a sample at the point where the error was largest at the previous step. Then we repeat this, we see that the error is too large here at the endpoint. And then we go on like this until we are satisfied. And the error is globally below, uniformly below the tolerance that was set by the user. Now, of course, you can see many problems with this. This algorithm will never be practicable because, like, first of all, we need to maximize the error over the whole interval. But of course, U is not known explicitly, so we cannot do this. So the thing that people do is, well, instead of maximizing over the whole interval, let's just maximize over a very fine but finite test set. So just take lean space with 1,000 points, for instance. But of course, like if you want to maximize this quantity over the whole test set, you need to know U over the whole test set, which of course is way too expensive. If we have taken all the samples over the test set, might as well use them all, right? Why are we doing greedy anyway? So what people do is to move from the strong greedy algorithm, where you look at the error as an indicator on where to add the next step, to a residual-based estimator. So essentially, we just take the equation and we just look at the residual of the equation instead of the error. And this, you can imagine, is much cheaper because at omega test, we don't need to evaluate the function u, we just need to be able to evaluate residuals. And in the reduced basis case, actually, there's advanced techniques to speed up even the computation of such a residual. And this is basically the state of the art. It's very simple, but it's basically state of the art of how the weak greedy algorithm for a reduced basis works. Now, this is just a summary of many of the things I just said. One of the things I would like to underline at this point is that the main disadvantage of this kind of methods is that it is intrusive. Okay. On one side, first of all, we need to access the system state u. We cannot build a model just from samples of the quantity of interest because we need to compute this projector, and the projector is built from the column from values of u. And the second thing is we need to perform the projection. So essentially, we need to access the system blocks to compute their projected versions, their reduced versions. All right. Now, let's move now to non-intrusive surrogates. And essentially here, again, many people have worked on this. And what I will present is just an overview of some of the standard methods for non-intrusive surrogate modeling of frequency domain problems. So here, to understand how we build a non-intrusive surrogate, we have to go back a bit more. We have to remember that the quantities we're actually approximating have this kind of structure, if you remember. And the structure that you see here, assuming that, of course, the right-hand side and the measurement operator depend in a smooth enough way on omega, we can conclude basically that u and y are meromorphic. And this justified in the electrical engineering community in the 90s, the effort of trying to find a rational approximation of the quantities u or y, mostly y in the electrical engineering community because of this non-intrusive business carried out by measurements as opposed to simulations. But anyway, the point is that we would like to set up a problem like this, where we try to minimize the error between a certain rational function r and the quantity we're trying to approximate y. And you see here, we're just computing the lowercase L2 error at all the sample points omega j. Now, this problem is complicated to solve because the set over which we're trying to solve this problem is not even a linear vector space. So you can imagine that there are some complications here, but let's forget them for a second. We've seen already in Francesca's talk that essentially the degrees m and n that we can achieve with our approximation are somehow limited by the number of samples that we have. And this is like a preliminary observation. In a ballpark way, we need to have at least as many samples as the sum of the 2 degrees plus 1. Okay, and this is going to be important later on. Now, how do we solve this problem? Well, first of all, we have to decide how we're going to represent our rational surrogate. And historically, in the 1800s, when all the rational approximation research started, everybody was using monomials, but of course, we cannot do computations with those. So people very soon went on to general polynomial bases. And you can see here that we can use different polynomial bases above and below to account for differences in the degree. But more recently, like another kind of representation gained traction. For now, I'll call it like Lagrangian basis representation. I will give you the actual name in a minute. But essentially, you can see that here, what we're doing is we're choosing a very specific kind of polynomial basis, which is a Lagrangian-like basis. In numerics 101, the kind of Lagrangian basis that you study is a very close relative of the one that you're seeing here. So a couple comments. First of all, I'm not normalizing the Lagrangian basis. So in the Lagrangian basis, we have omega minus omega k divided by omega j minus omega k, but here we don't have it. And the reason is that in rational approximation, the normalization is automatic, because if we don't normalize above and we don't normalize below, everything works out. And the second thing is that I'm using the same notation for the support points as for the sample points, because the support points are usually chosen as a subset of the sample frequencies. So without loss of generality, we just assume that the first t points are both sample and support. Just notation. Now, I call it Lagrangian basis because we have a Lagrangian-like interpolation property, which tells us that if we evaluate our our rational function, at one of the sample point, at the support points, I should say, then we recover exactly the ratio of the coefficients. So this is what happens with Lagrangian interpolation. But now, I mean, your question might be, but everybody knows the Lagrangian basis sucks because of conditioning issues. Well, turns out that for rational approximation, this is not a problem. So instabilities are not a problem. And I would like to explain to you in just 2 algebra steps. So first of all, you see that the product above and the product below are both missing the jth term. So we just add it and we divide by it. We're not doing anything weird here, but then we just can simplify the nodal polynomial and we're set, right? We don't have any more ill-conditioned nodal polynomial here. We just have a weird non-polynomial representation of a rational function, but everything works out and it can actually be proven that this barycentric representation of the rational function has very nice numerical properties. I will not go into the details, but if you're interested, there's many references that I can give you. Now, given this, let's try to come up with an algorithm for non-intrusive approximation. The beginning is the same as before. We need to take the samples of the quantity we're trying to approximate. And for starters, I will consider the quantity y. Then we need to fix a denominator degree, which essentially is going to tell us how many coefficients are going to be needed for the denominator. Because the coefficients in the numerator, we set them by hand in such a way that we achieve interpolation at all the support points. So if you see here, because of the Lagrangian property, we are guaranteed to recover exactly the values of y at all the support points omega j. All that's left is to find some good choices of the coefficients q1 all the way to qn plus 1. And for this, we just impose interpolation conditions at all the points that we've not considered yet. So essentially, we take our S samples, we split them into support points and test points. We define the rational surrogate based on the support points, but then we find the coefficients using the test points. Fairly easy. And you can see here that this Loewner matrix appears, and essentially the coefficients are found by finding an element of the kernel of this Loewner matrix. All right. So all of this works. And of course, in case of experimental data, we might have noise. So there is a least squares version of the same kind of algorithm. Essentially, we take less than half support points. But more importantly, I guess, we can find a Loewner approximation also of the state U. For fairly technical reasons, we cannot have, okay, if we want to approximate the function U, then we cannot not do least squares. Essentially, you just look at the number of degrees of freedom that you have in approximation. You cannot, you have an overdetermined system, so you cannot not do least squares. And this is the kind of system that we have. We have a very tall and skinny Loewner matrix, and we're trying to find essentially an element of the almost kernel of this tall and skinny matrix. And this we do by SVD. Simple enough. Now, the real question now is, okay, all of this works, all of this is non-intrusive, but can we make it reliable in the sense of being able to identify on the fly how many samples we need to take and where to take them? So can we develop an adaptive algorithm for Loewner approximation? And of course, if we look at this at a strong greedy for the function y, we have the same problem as for reduced spaces, because if we know all the values of y at all the points in the test set, then well, I mean, what's the point of doing a greedy anyway? You might as well just do least squares Loewner with all the data that you have. We cannot do weak greedy for y because we don't have a residual equation for y. Okay, y is just a functional, right? We cannot write a residual for it, but we can do weak greedy for the quantity u. Now, to do the weak greedy in the same way that we did it for reduced spaces, we need to have to be able to evaluate the residual, which of course is not non-intrusive. So this is an intrusive algorithm at its core, in some sense. We need to be able to evaluate the residual to be able to decide where to take the next sample and how to improve at best the current surrogate. All right, and I will come back to this in a second because there is a kind of a solution to this problem, as we will see. Now, this is a summary of everything I've said about the non-intrusive case, and the main aspect that I would like to underline here is that the Loewner framework and non-intrusive algorithms in general have the problem of not being sample efficient, in the sense that if I want to approximate n resonating frequencies of the problem, we need to take at least 2n samples. And this is something that we've seen also in Francesca's talk this morning. Now, this is where we started from, essentially, when we asked ourselves the question, can we make this, can we improve on this, okay? And this is what the method that we developed, minimal Russian interpolation. And this is the same information that I've been bombarding you with the whole talk. Essentially, it's summarized in a table. if we are looking for an approximation or for a surrogate model for a frequency domain problem, we can either do POD reduced basis, for instance, and in this case, we have to do intrusive projection, but we are very good at our approximation quality in the sense that with S samples, we can approximate an S resonating frequencies of the problem, S peaks of the graph. Instead, if we do a non-intrusive approximation, we are building our surrogate by interpolation, so we're being non-intrusive, but the price to pay is this effective efficiency of the method. Essentially, if we want to approximate 10 resonating frequencies, we need at least 21 samples. And what we were trying to do is we try to put a last column in this plot, in this table, and we try to have a method that is non-intrusive but has a better efficiency in terms of samples. And this is what we get. So if we look at the minimal Russian interpolation that we'll define in a second, we are non-intrusive in the sense that we don't need to perform this projection, but we achieve an approximation effectiveness that is almost as good as the one for reduced basis. So essentially, if we have 10 samples, we can approximate 9 poles. And this -1, you might ask, like, why is there a -1 there? Can't you get a quality that is exactly as good as the reduced basis method? And the answer is no. The -1 essentially is the price that we need to pay for non-intrusiveness. Okay, so we cannot get rid of the -1, unfortunately, unless we come up with a method that is a bit more intrusive than what we would like. Now, the idea is, like, the way we increase the efficiency of minimal Russian interpolation is by removing the necessity for the test points. If you remember, in the Loewner framework, we had the sample points. We need to split them into support points and into test points. The support points define the surrogate, and the test points are used to find the coefficients of the surrogate. Here, we just need to find a different way to find those coefficients, and that is going to essentially cut the cost in half. We don't need the test points at all. And the way we do this is, well, this is the algorithm. I think it's the easiest way to show it to you. As I said, all the sample points are support points. We don't have any test point here. We build our surrogate just like before. And the way we find the coefficients, Q1 all the way to QS, is going to be by minimizing something completely arbitrary at first. So the way we find the coefficients, Q1 to QS, is we minimize the norm of the surrogate for large frequencies. Okay, so we just look at this quantity. We let the frequency go to infinity. It's a complex number, so it could go to infinity in all directions. But anyway, we try to minimize this guy. Okay, and this is the way we find the coefficients Q1 all the way to QS. And well, first of all, let's try to understand how we can do this. Well, simple enough. You do a bit of linear algebra and linear algebra, and it turns out that actually what you're after is just the solution of a linear system. A very simple linear system where the right-hand side is just a vector of ones, and the matrix that we need to invert is the Gramian matrix that we had also in reduced basis. Okay, so the Gramian matrix makes a comeback. We need to invert it, and this applied to the vector of all ones is going to give us our vector of coefficients. Magic. Okay. Anyway, the point with one of the problems that we see in practice is that this Gramian matrix is often ill-conditioned, also because the samples are, the samples can vary widely in magnitude because we might have certain resonances. And the way we solve this is by making this problem a bit more numerically stable. Instead of solving the system, sometimes we find the denominator in a slightly more robust way. Instead of solving the system, instead of finding this inverse of the Gramian matrix, we just compute an SVD of the Gramian matrix, and we take the least important singular vectors. And these are going to give us an approximation, something that is close enough to the actual Qs that we're after numerically. Now, why should this make sense? Well, if you think about it, in many applications of interest, like the ones I showed you at the beginning, you can actually prove that the function U vanishes if you take infinitely large frequencies, as long as you take the right path of frequencies. Remember, we're in the complex plane, so we can take many different paths. And just to give you an idea of what this might look like, okay, so if your system is finite dimensional, then yes, of course, all the eigenvalues are going to be inside a compact. So outside, this expansion is gonna converge to 0 under some regularity of the pencil, of course. If you have the cavity problem, you know that all the eigenvalues are actually on the real line. So as long as you move in the other direction, it's all good. And in the scattering problem, all the eigenvalues are below the real axis. So as long as you stay above, this property is also guaranteed. So somehow this idea of a function that vanishes for large frequencies in some directions is guiding us in choosing some good surrogate coefficients. All right. So just to answer the next question, of course, because I've asked it for all the methods, can we develop a greedy algorithm, an adaptive algorithm for minimal Russian interpolation? And the answer is kinda, in the sense that we can set up exactly the same kind of algorithm as for the weak greedy Loewner framework, but we're still left with the problem that evaluating the residual is intrusive. So what we did what I did in my PhD was actually to find out that the dependence of this, I mean, the structure of this residual is actually simpler than you might imagine. So we have this kind of, if you want, it's a theorem. It's simple enough. You can just prove it by algebra autopilot, essentially. If you have a system in the form of a linear time invariant system where the right-hand side doesn't depend on omega, you can actually show that with respect to omega, the residual is equal to a constant times the denominator to the -1. So essentially, if you plug into your equation a surrogate that is in barycentric form, okay, then you know exactly how the residual norm will depend on the frequency omega. The only thing that's left is identifying this constant C, because I mean the constant C is going to tell us how large the residual is, and unfortunately you cannot identify C non-intrusively. Okay, so essentially we're just pushing the problems under the carpet. But if you think about it, this kind of expansion allows us in a non-intrusive way to compute the next point to add to our approximation. Because remember, what we're after is just the argmax, not the max. Okay, we're just after the argmax of this function, and if we know how this function depends on omega, we can just rephrase this maximization of the residual into a minimization of the denominator, which is nice. And I want to mention, because like for transparency, I guess we can apply the same kind of reasoning also to reduced basis and to least squares Loewner. So this is a way to make the least squares Loewner weak greedy method practicable, in the sense that even in a non-intrusive setting, because we can use this kind of estimator to drive the adaptivity. All right, so I would like to show you some numerical experiments just to underline some of the things I've discussed so far. The first one is a very simple experiment. It's a synthetic experiment. And what I'm doing is I'm just looking at the approximation error of my surrogate as I increase the number of samples, okay? Don't think too much about what this should mean. I'm just trying to tell you a very simple story, which is if you use reduced basis or minimal Russian interpolation, the error decays essentially in the same way. But if you use the Loewner framework, you're limited by this sample inefficiency, in the sense that the decay rate of the error for Loewner is going to be the square root of the decay rates for the other two, because we need twice as many samples to achieve the same error. And of course, we can choose to apply our greedy methods for our reduced basis or for MRI, and you see that both of them behave in a similar way. But of course, all the curves that pertain to MRI here were obtained non-intrusively, okay? And okay, this was a particularly simple example, but still, it shows that we can achieve a very competitive result without being intrusive. And if you wonder why MRI is better than reduced basis, we can talk for several hours about this. But that's a topic for a different presentation, I guess. All right. So a more interesting example, especially for this kind of audience, it's we're considering an exterior scattering problem with this trapping scatter here. The problem is the one you might expect. We truncate the problem in a sufficiently large ball, and we impose a very crude Robin approximation of the Sommerfeld radiation condition. We apply the greedy algorithm with our estimator that we derived before. Problem is, of course, here we're not in the setting that where the theorem applies, because, well, for one, the dependence on the frequency is quadratic; it's not linear. And secondly, the frequency appears also in the right-hand side. So neither of the two assumptions of the theorem were satisfied. So, but we still apply the indicator heuristically, and we try to see how good the results are. Now, the algorithm starts from the two samples that you see at the two endpoints of the interval, omega equal to 10 and omega equal to 20. These are the two snapshots corresponding to those. And we use finite elements to find them, just on a sufficiently fine grid. This is the estimator that we had. You see that the error goes to 0, of course, at the points that we've already sampled. And then we have this profile that tells us, look, the largest value of the error is going to be at 13.8, whatever. We take the sample there, and then we proceed. By the new point, next point, on and on and on. And at some point we stop when we reach the 50-second sample, and we see that actually the algorithm thinks that it has achieved that the tolerance is attained everywhere. Now, is it actually the case? Not really, in the sense that this is the reconstructed norm of the solution. The blue is the surrogate, and the black dots are some validation points. And the green dots are the sample points. Okay? And you see here, if you look below, this is the relative error, which is the quantity we're trying to keep below the tolerance. And it's almost everywhere below the tolerance, but not exactly. And this is because we are using an indicator and not an estimator. Okay, this is just an indicator of where we should sample. It doesn't guarantee that the error is actually going to be below the tolerance everywhere. And this is kind of a negative answer to the title of my presentation. We cannot really be truly reliable if we want to be completely non-intrusive. Now, one thing I would like to underline, and then I will conclude, is that this plot I'm showing is showing only the normal view, but of course we can try to see how the minimum Russian interpolation algorithm is approximating the solution itself. So you can see here, this is the exact solution, and this is the surrogate solution at some point omega equal to 12. You can see the approximation in the eyeball norm is good enough. If we look at some of the lower peaks, remember the peaks are just an indication that in the complex plane, if we move a bit below, I want to say, the real line, then we're going to have a resonance. And you see here that we have a trapping mode corresponding to that, okay, which is related to the question that Christoph was asking this morning. And of course, if you look at the largest peak, we're going to have a very large trapped mode. And you see, if you look at the magnitude, it's like 24. So you see, it's an almost, right? It's a quasi-resonance. All right, so some of the conclusions I would just like to underline some of the features of the three classes of methods that I presented. So if you use a projective approach, the advantage is that you're using the sample points, the sample values very optimally, almost optimally, because you're doing a lurking projection. But the problem is that we cannot always do that. We need to be intrusive, and we need to assume simplified dependence on the parameters, which is something I have not talked about. But if you've ever applied reduced basis yourself, you know that this is a problem, especially for scattering problems where the forcing term is harmonic in frequency and space. This can be an issue when you try to perform a reduced basis approximation of the solution of a scattering problem. If you take a non-intrusive method, you can apply them with very high generality. But the problem is that they're not exactly sample efficient. We need to sample more than a reduced basis method would need to. And somehow minimal rational interpolation, minimal rational approximation tries to get in between those two. It tries to exploit the samples more optimally, but somehow there is an assumption that is we need to be able to compute this Gramian matrix. Okay, and that's as intrusive as I want to get, essentially, in my algorithm, because I want to have the data. Because if I don't have the data, I cannot construct the model. But even given the data, it might not be possible to construct the Gramian, because the Gramian are inner products, right? And inner products might be something that's intrusive to compute. So this is kind of where we got, and this is, at least in my opinion, non-intrusive enough for many applications. And yes, the other problem is that, of course, if we want to use the non-intrusive estimator for adaptivity, we need to be a bit careful, because it's an indicator, it's not an estimator in the sense of the word. Now, to conclude, if I okay, I'm just going to give you I'm just going to give an idea of how the parametric case might work, and I will just give this picture, I guess. So the idea is that we want to build upon what we did in the non-parametric setting, where only the frequency is taken into account. And you can imagine that the methods that I described so far can give you an approximation with respect to frequency if we keep the parameters fixed. Essentially, we are able to obtain an approximation of each of these colored curves using the methods that I gave you. Even in the greedy version, you can do very fancy stuff as long as only the frequency is allowed to change. Then how do we build a surrogate with respect to frequency and parameters? Remember that here I have only one parameter, but we might have many. We might have hundreds of parameters in UQ. Well, the idea is that we take all these fibers that you see, and we just combine them, okay? So we try to fill the gaps between them. And to do that, I mean, I can refer you to the presentation I gave in the other workshop, but the idea is that we need to be careful because combining rational functions is not as easy as it might seem. All right, with this, I would like to conclude. Thank you all for your attention.